Welcome back to The Explainer. So, have you ever stopped to wonder where the sun, the earth, and, well, literally all the planets around us actually came from? Because today we are going on a massive journey. We're heading 4.6 billion years back in time to witness the very birth of our solar system. And honestly, the true story here is way more dramatic than any sci-fi movie. Okay, let's dive right into this. To really get it, we need to completely reset our minds and our expectations. Just imagine a very specific place in our Milky Way galaxy that is entirely dark and freezing cold. No sun, no planets, absolutely no light. Just a gigantic floating cloud filled entirely with gas and cosmic dust. It's peaceful, it's quiet. But as you'll see, there is no way it was going to stay that way.
Chapter 1. The Cloud and the Spark.
So our quiet little solar nebula needed an inciting incident to wake up, right? And that came in the form of an immense cosmic shockwave triggered by a supernova. We're tracking an incredible journey here, going from that initial incredibly violent blast 4.6 billion years ago, pushing through a highly active 100 million year formation period, all the way to the stabilized solar system we call home today. It's really this sweeping story of total chaos slowly transforming into order. And right as that shockwave hits, we see something pretty elegant in action. It's called the nebular theory. Historical thinkers like Kant and Laplace actually first conceptualized this brilliant idea. Basically, it's the concept that this cosmic cloud, once it gets forcefully nudged by the shockwave, starts to collapse inward. And it does this under the sheer force of its own gravity. The more it collapses, the denser and more active the whole thing gets. And this brilliantly illustrates what happens next. Think of a figure skater spinning on the ice. You know how when she pulls her arms in really tight against her body, she spins so much faster? Well, the collapsing cosmic cloud did the exact same thing. As it contracted and pulled inward, its rotation rapidly accelerated. It literally flattened out from a giant sphere into a spinning disk. It's almost like a giant batch of cosmic pizza dough being twirled out in space. Chapter 2. The Birth of the Sun. So right at the very center of that spinning, flattened disk, matter was piling up fast. The pressure and the heat in this central core kept accumulating to these just extreme levels, eventually crossing a critical threshold. And boom, a colossal nuclear furnace ignited. Hydrogen atoms were smashing together, fusing into helium, and releasing a blinding amount of energy. And in that continuous flash of light and raw power, our proto-sun was officially born. Now, our young sun is basically acting like a giant, intense radiator right in the center of the solar system, completely illuminating all that surrounding dust and gas of the disk. But right next to the sun, the heat was absolutely torrid. I mean, it was so hot that only the toughest, most heat-resistant materials, we're talking heavy rocks and dense metals, could even survive without just being vaporized on the spot. Chapter 3. The Frost Line. Let's move a bit further out and see how this builds. As we travel away from our fierce new sun, we can actually see how the distance completely changes planetary construction. We cross this absolutely crucial invisible boundary called the frost line. This is the exact distance from the sun where the ambient temperature drops low enough that freezing actually becomes possible. Out here, lighter gases and water don't get burned away into vapor. Instead, they successfully condense into solid ice. Crossing this line totally changes the raw materials we have available for building planets. So inside the frost line, close to all that intense heat, tough rocks and metals stuck together like sticky crumbs. And that's what formed our dense, hot, rocky terrestrial planets: Mercury, Venus, Earth, and Mars. But outside the frost line, well, it was cold enough out there to build these massive rock and ice cores. And these cores had such strong gravity that they were able to sweep up enormous amounts of gas. And that is exactly what gave birth to our massive gas giants: Jupiter, Saturn, Uranus, and Neptune. Chapter 4. Building the Planets. Okay, so how exactly did these space crumbs and icy cores become massive, full-blown planets? The core mechanism at work here is a process called accretion. Sure, it sounds like a formal scientific term, but honestly, it works just like rolling a snowball down a snowy hill. As the snowball rolls, its sticky surface and increasing weight allow it to pick up more and more snow, growing larger and larger. Out in the vacuum of space, gravity is doing that sticky work. It's pulling floating materials together to accumulate mass over time. The whole progression is pretty wild. It starts with just microscopic grains of cosmic dust.
Then those clump into small pebbles, the pebbles gather into larger rocks, and eventually they become these massive boulders several kilometers across, which we call planetismals. Imagine these giant planetismals violently crashing into each other, fusing into protoplanets, which then eventually clear their orbital paths to become full-fledged planets. The scale is just mind-blowing.
Now, according to sophisticated models from sources like Lumen Learning, this entire chaotic cosmic construction site, from those microscopic specks of dust to the full-size planets, took about 100 million years to complete. Now, to us humans, 100 million years sounds like an absolute eternity. But in the grand timeline of the universe, that is literally just a blink of an eye.
Chapter 5, The Great Cosmic Billiards.
Now, it's really tempting to just think the early planets sat peacefully in these perfect little orbital circles growing over time. But recent studies published in Astronomy and Astrophysics paint a much different picture. It was a violently chaotic system. The giant planets, especially Jupiter, did not just stay put. They actually danced gravitationally. They migrated inward toward the sun and then drifted back out again. This violent cosmic billiards game threw rocky debris everywhere, sculpted the final architecture of our system, and may have even stunted the overall growth of Mars. Just incredible.
Which, of course, begs a really big question. What happened to all the leftovers? Because, let's face it, not every single piece of rock, dust, and ice successfully made it into a major planet. There were literally millions of pieces of planetary construction debris just floating around the sun.
Well, these leftovers ended up forming some very specific neighborhoods in our system. Take the space between Mars and Jupiter, for instance. The gravitational bullying of Jupiter actually prevented a whole ring of debris from coalescing into a planet, and that left us with the asteroid belt. Then, way out beyond Neptune, we have this massive ring of frozen, icy debris called the Kuiper Belt. And finally, there are the comets, these fascinating, highly eccentric wanderers made of mixed ice, rock, and dust. They're essentially just giant, dirty snowballs.
But here's the really crucial point. As Britannica data suggests, these leftover comets were not just some beautiful celestial fireworks display. During those chaotic early days, comets were actively bombarding the young Earth, and in doing so, they very likely delivered the water that fills our oceans today, along with complex organic molecules, the essential building blocks for life itself. They were, quite literally, our cosmic delivery system.
Chapter 6, Equilibrium and Earth.
Finally, after millions of years of chaotic collisions and wild planetary migrations, the frenetic energy dialed down. Those wild orbits finally stabilized, and our hard-won, modern solar system emerged. We got one brilliantly shining star at the center, 8 distinct, beautiful planets, vast belts of ancient debris, and a myriad of gorgeous moons and wandering comets. It really is a system born from profound chaos that managed to settle into a precise, fragile balance. And thankfully for us, a balance that just happened to be absolutely perfect to harbor our small, blue, rocky Earth.
Which leaves us with an incredibly provocative question. Once this perfect cosmic stage was fully set, how did life actually spark and appear on this tiny rock? We're going to dive into that mystery in our next explainer. If you loved taking this epic 4.6 billion year journey with us today, make sure to like and subscribe so you don't miss the next step of our adventure. Keep looking up, and we'll see you next time.